A very good morning, ladies and gentlemen. I'm Sam, your presenter for today. As we all know, Sarawak is a fast developing state in Malaysia with many ongoing construction projects. Meanwhile, in recent years, the focus on environmental sustainability has been increasing. Hence, my research topic for today, which is the environmental life cycle assessment of concrete with different mix design in Sarawak, Malaysia. So this is the presentation outline for today, which consists of these 8 different sections. First, Lee 2020 stated that the building sector is one of the largest greenhouse gases contributor. Not to mention, within this sector, the cement manufacturing industry is the main contributor of global carbon dioxide emission. Next, for the problem statement, basically it can be summarized into 3 problem statements for this research. First, what is the environmental impact of manufacturing ordinary Portland cement concrete in Sarawak? Second, what are the environmental effects of supplementary cementitious material on concrete? And finally, what is the optimum mix design in terms of environmental performance? As for the aim and objective of this research aims to evaluate the environmental impact of using different SCMS as partial replacement of cement in Sarawak. To achieve the aim, several objectives have been listed, which includes identifying the environmental impact of OPC concrete and concrete with different supplementary cementitious material, identifying concrete mix design with the least environmental impact, and study the possible advantages and disadvantages of different concrete mix design through a life cycle assessment. Alright, next for the literature review. So what is a life cycle assessment? Basically, a life cycle assessment is a comprehensive framework which allows systematic analysis of the potential environmental impact of products or services. According to ISO 14040, LCA can be divided into 4 main phases, which are namely goal and scope definition, life cycle inventory, life cycle impact assessment, and life cycle interpretation. Okay, next. The system boundary is the conceptual line that divides the study interest from everything else. Generally, there are 2 types of system boundary, namely cradle to gate and cradle to grave. A cradle to gate limits the boundary starting from the effects of raw material extraction, transportation of materials, material processing, and other processes until the finished product leaves the gates of the factory. On the other hand, a cradle-to-grave approach accounts of the impact over its entire life cycle, which includes the operational phase, treatment for end-of-life material, and final disposal. So many LCA studies have been conducted on concrete. However, most peer-reviewed journals are not based for Sarawak, Malaysia. As PTEC 2014 stated, building material choices are usually selected locally. The transportation distance and electrical usage and material properties undoubtedly will differ and hamper the results of the assessment. Alright, next, the methodology. First, for the LCA tools, the software OpenLCA version 1.1 has been selected to be used for this life cycle assessment. As for the database, the Ecoinvent 3.7 LCI database has been selected as it is one of the databases recommended by many authors. Now, for our system boundary. So a cradle-to-gate approach has been selected, as you can see over this figure here. This approach is preferable because in this case, data regarding operational phase and end-of-life phase is limited. To mention, the manufacturing of cement is recognized by several authors as the most energy-demanding and high-pollution segment. 5 mix designs have been proposed as shown in this table here. M1 represents the ordinary Portland cement concrete, while M2 to M5 represent concrete with different percentages of LCMS. Here are some of the input of material to produce 1 cubic meter of grade 35 megapascal concrete. And here are some of the flows selected in OpenLCA to simulate the concrete manufacturing process. Next is the assumptions made for life cycle assessment. First, performance indicators such as durability and workability of concrete are assumed to be approximately identical. Fly ash and GGBFS, which represent ground granulated blast furnace slag, are considered as a byproduct, and hence the energy used for electrical and steel production will not be considered within the system boundary. A lorry of 16 to 32 metric tons capacity with Euro 3 emission standard is assumed to be used in this study. Another important estimation is the transportation distance. A safety factor of 1.2 is applied to the distance obtained to simulate the emission for the trip back. Alright, let's discuss about some results. Here is a relative indicator results of each mixture. So the percentages you see over here is relative to the highest output. Overall, there are two common trends across the indicator. So for acidification potential and global warming potential, the mixture 1 have the highest environmental impact. However, for indicators such as depletion of abiotic resources, eutrophication, and human toxicity, mixture 2 have the highest environmental impact. Alright, let's look into global warming potential. So global warming potential is an index for measuring a substance's potential contribution towards global warming. It allows comparison across different gases in relative to the emission of 1 kilogram of carbon dioxide. So in this table, mixed design involving SCMS showed a reduction in global warming potential. In relative to mixture 1, the other mixture performed 16 to 44% better. Interestingly, M4, which uses blast furnace slag, performed better than M3 at the same percentage replacement of 25%. Human toxicity potential is another important indicator for evaluating potential damage from a unit of substance. This indicator allows comparison of human toxicity potential across different materials in relative to the emission of 1 kilogram of 1,4-dichlorobenzene. Interestingly, M2 have the highest HTP than the reference mixture M1. This might be caused by the extra process required to process the fly ash. However, as replacement percentages increases, the HTP decreases as shown in mixture 2. M4 and M5 showed significant improvement when compared to M2. To conclude this presentation, concrete with less environmental impact can be achieved through modifying the mix design. Moreover, incorporation of SCMS in concrete mix design is effective in reducing environmental impacts. Higher percentage replacements such as M3 and M5 consistently perform approximately 10 to 20% better when compared to lower percentage replacement variable. GGBFS is preferred over fly ash as it has more potential in terms of achieving a higher replacement ratio. In terms of future work, a cost analysis is important to help us understand the relationship between economics and environmental impacts, hence developing an eco-efficient design. Experimental works can also be carried out for actual calibration of the input material and provide evaluation to the technical performance of concrete. Alright, that's all for my presentation. Thank you everyone.